Snow removal costs up to $3 per ton. The ultimate in snow removal is to keep snow from drifting on the road in the first place. Permanent snow fences with a lifespan of 25 years can cost as little as 3 cents per ton for snow storage, as compared to $3 for removal. Where else can maintenance investments have the potential of a 100-to-1 return? If snow drifts are a problem to you, some new information on snow fence control is presented in this video. In Wyoming, state officials solved a serious drifting problem along Interstate 80, where 45 to 65 mile per hour winds are common. They demonstrated conclusively that properly engineered fences can be cost-effective in eliminating drifts and improving road conditions. Highway agencies and other organizations spend billions on de-icing and snow removal every year. Blowing snow adds substantially to the cost of winter maintenance and represents a serious hazard for motorists. In this presentation, we'll demonstrate the dramatic effectiveness of properly engineered snow fence systems. The presentation is divided into two parts: benefits of snow fences and key elements of effective snow fences. We'll cover benefits first. Properly designed snow fences virtually eliminate the need for continual removal of snow drifts, resulting in potential returns of 100-to-1 on maintenance investments. They also reduce pavement maintenance costs, improve highway safety, and increase visibility. The most effective snow fences range in height from 6 to 16 feet and include improvements to shape, size, and design. Fences less than 6 feet typically do not provide effective storage capacity or trapping efficiency. Materials include wood, plastic, and composites. Fences are designed to incorporate the latest guidelines from sharp research on blowing snow control. Two types of snow fences are used: those that collect snow and those that deflect snow. This presentation covers only collector-type fences. Researchers have gained new insight into the process of blowing snow. They developed and tested new guidelines for drift control. These tests proved that properly designed systems could eliminate the need for removing drifting snow, improve highway safety, and reduce pavement maintenance costs.
Where we had great, huge snow encroachments on the road before the fence, after the fence, we had no encroachment on the road. By virtue of keeping the snow off the road, we have reduced our maintenance costs tremendously. We simply haven't had to go out there and plow as much snow, push it around, because we've stacked it off the highway right away. In terms of economy, we can store snow for about 1/100th of the cost of pushing it around or plowing it. The other advantage that we probably didn't think of initially was that by virtue of taking the snow out of the air, we also improved visibility.
A 10-year study has shown that snow fences can significantly reduce accidents caused by poor visibility due to blowing snow. On a test section of Interstate 80 in Wyoming, data showed a 70% reduction in accidents in areas where fences were constructed to reduce blowing snow conditions. Safety is also improved by keeping guardrails, signs, and delineation posts free of snow. Snow fences reduce the amount of water that can seep under pavement, resulting in less cracking, heaving, and overall maintenance. Snow fences are also useful in such areas as airports, pipelines, and electrical substations. This is an aerial photograph of one town in Alaska with a serious drifting problem. Houses shown here were typically buried up to the roof, as you can see in this close-up. A 15-foot wooden fence placed on the edge of town eliminated drifting snow around the houses, improving access for deliveries and emergency equipment. These are a few of the direct applications of modern snow fences. With new reference materials and design guides developed through SHARP, design of a highly effective snow fence system is relatively simple. Based on this improved understanding of blowing snow and drift control, government agencies can significantly reduce winter maintenance costs and improve public safety. In this second part, we'll discuss how fences work and key design elements. First, let's cover how fences work. Snow fences reduce wind speed, causing most snow to fall in an area behind the fence. But some snow is also deposited on the upwind side of the fence. After coming to rest, the particles begin to freeze together, so they aren't as readily picked up by the wind again. In the initial stage of drift development, snow particles are deposited downwind within an area 15 times the height of the fence, or 15H. When the drift has moved out to about 20H, the fence is about 75% full, and the drift profile becomes smooth. In the last stage, growth occurs more slowly, out to about 35H. To develop an effective fence system, you need to understand the key elements. These are capacity, height, design, and placement. Collector fences are designed for snow storage. A very important factor is how much snow the fence must collect. That depends on a combination of factors: wind frequency, velocity, and the amount of snow. Little snow transport occurs above 16 feet. Why? Blowing snow particles are mostly pure ice. The largest ones creep along the surface. The result can be snow waves or dunes. Particles that are slightly smaller, but still too big to be suspended, tend to jump along the surface. Wind speed has a big impact. The amount of blowing snow below 16 feet increases with the fourth power of the wind speed. In other words, a doubling of the wind speed causes a 16-fold increase in snow transport. Snow transport can be estimated from wind speed and direction, extent of open area, and snowfall. In areas where the ground remains snow-covered throughout the winter, transport can be estimated from wind speed records. Another method of estimating snow transport is to determine the fetch, or length of open space upwind of the proposed snow fence location, and the quantity of snow relocated by the wind. By taking evaporation into account, it is possible to compute the quantity of snow transported per unit width across the wind over an entire winter season. Knowing how much snow a fence will hold, or its capacity, it is then possible to calculate the height of a single fence or the number of rows of fence needed to store the estimated seasonal snow transport. Let's look at some examples. Assume an area has a fetch of 3,000 feet, the total annual snowfall of 90 inches, and open terrain with plowed ground. Using the snow transport graph in the snow fence guide, approximately 38 tons of snow will be transported per foot of width across the field. Applying the 38 tons to another chart in the guide reveals that an 11-foot fence is required. With the same fetch and terrain conditions, but for different annual snowfall, a 28-inch snowfall would require a 6-foot fence. A 56-inch snowfall would require an 8-foot fence. And a 180-inch snowfall would require a 15-foot fence. The guide describes other factors that can be used to determine the appropriate height of fence to deposit blowing snow in adjacent fields rather than on the road. Although fences as tall as 16 feet may be needed in areas of high snow transport, such as Alaska's North Slope, 6- and 8-foot fences will provide satisfactory control in many locations throughout the Midwestern and Eastern United States. Whenever possible, fences taller than 4 feet should be used because of the greater storage capacity and trapping efficiency. The capacity of a snow fence greatly increases with a slight increase of height. For example, a 6-foot fence will store more than twice as much as a 4-foot fence. Having estimated the quantity of blowing snow that is crossing a location, it is possible to determine the height of fence necessary to store snow in the most economical manner. It costs less to build a single tall fence than several shorter rows with the same storage capacity. What's more, multiple rows of fences take more space, meaning greater easement costs. Finally, taller fences trap a larger percentage of the blowing snow. This means better visibility, especially in strong winds. When wind speed is less than 20 miles per hour, about 90% of the blowing snow is below 4 feet in height. However, if winds increase to 45 miles per hour, more than 30% of the snow is above the 4-foot level. Because snow passing over the top of a fence is not caught by the fence, it's clear that wind speed is an important factor in determining exactly what fence height is required. Inclining the top of a fence downwind has little effect on drift depth or storage capacity for angles up to 15 degrees. However, inclination of the wood fence shown here has advantages for construction and maintenance. The next key element to consider is the design of the fence. This covers dimensions, configuration, materials, and anchoring. An important consideration is porosity, the open area of a fence. Solid fences form much smaller downwind drifts than porous fences. Experiments show that fences in the range of 40 to 50% porosity form the largest drifts. The configuration of these openings has little effect on storage capacity, but fences having horizontal boards and bottom gaps are less likely to become buried. A bottom gap, 10 to 15% of the total fence height, is most effective in keeping snow from building at the fence and burying it. Buried fences are less effective in trapping blowing snow due to reduced effective height and storage capacity. You may need to increase bottom gap in some locations because of snow cover, vegetation, or irregular terrain. Fences can be constructed from a variety of materials. Wooden boards or plastic are the most common. Aluminum or steel will also work, but are more expensive. For permanent fences, the horizontal board design as used along Interstate 80 in Wyoming has proven effective and economical. It is made of 1 by 6 inch horizontal boards with 4 to 6 inch spaces in between. Boards are fastened to trusses made of 2 by 6s and 2 by 8s. U-clamps or angle clips are used to anchor the trusses to 3/4 inch diameter rebar, driven solidly into the ground. U-clamps are preferred, but angle clips will work. Firmly anchoring the fence is very important. Rebar penetration depth depends on local soil conditions. For good soils, 3.5-foot burial is adequate to hold a fence as tall as 14 feet in 100-mile-per-hour winds. 2.5 feet of burial is adequate for 6 to 8 foot high fences. Less anchoring depth is required in lower winds. All fences must be tightly fastened to the anchor rods. This design is typically used for heights from 6 to 14 feet, where fences can be permanently located on open rangeland. During the last 5 years, construction costs for this type of fence have averaged less than $1 per square foot of fence surface area. Plastic fencing can be as effective as wood and offer advantages for pole-supported type fences. Pole-supported fences minimize the area occupied by the fence and are better suited for steep terrain and permafrost soils. Plastic is good for fences with supports spaced 12 to 16 feet apart where lumber would sag. In locations where space is limited or fences cannot be left up year-round, portable fences 6 to 8 feet tall can be made from wood or plastic. A 100-foot length of 8-foot fence, like the one shown here, can be installed or removed in 1.5 hours by a crew of 2. This 200-foot fence can be stored in an 8 by 10-foot space. Properly constructed and maintained, any fence should last for 25 years. For any fence system to last, periodic maintenance must be performed to ensure the highest level of service. This means that fences must be checked periodically, and broken or missing pieces must be replaced. Also, anchoring systems must be checked and tested to ensure that the fences are secure and will not blow over. The final element is placement. No matter how a fence is constructed, if it is not placed properly, it may do more harm than good. Because drifts may extend in length as far as 35 times the height of a fence, the fence should be at least that far from the roadway. For example, proper placement of a 6-foot tall fence would be 35 times 6 feet, or 210 feet from the edge of the roadway. In irregular terrain, however, it may be necessary to place the fence even further from the road. Length is an important dimension in placement of fence systems. At the end of a fence, drifts are rounded by the wind. This end effect reduces storage capacity, so it's necessary to build a fence longer than the area you wish to protect. Where an opening is required, it should be protected with another fence upwind. Multiple rows of fences should be spaced 25 h apart to avoid burying other downwind fences. Generally, fences should be perpendicular to the prevailing wind, but if winds are within 25 degrees of being perpendicular to the road, then the fence should be parallel to the road. Staggering the rows of fences may be necessary to protect long reaches, but the distance between the road and fence should not exceed 70 h. Staggered rows must be sufficiently overlapped to prevent the wind from winding its way through the openings. Fences should extend far enough on either side of the potential drift area to account for variations in wind direction from perpendicular to the fence. Extending the fence length by 20 h on each end will take care of the natural variation in wind direction and the end effect described earlier. Prevailing wind direction is easy to determine by using a compass to measure alignment of existing drifts. A better method involves taking black and white aerial photographs. It can also be determined from weather data, since we know that snow transport is proportional to the fourth power of the wind speed. Let's review the benefits and key elements for design of an effective snow fence. Fences can reduce both maintenance costs and accidents. Also, fences eliminate drifts, improve visibility, and reduce road ice. To properly select, build, and use fences, you'll also need to remember some key guidelines. The best fences range in height from 6 to 16 feet. Those with 40 to 50% porosity trap the largest amount of blowing snow. A bottom gap of 10 to 15% is best. The horizontal board design is very effective, and proper anchoring is important. Also, taller, more effective portable fences can now be more easily transported and installed due to the new lightweight materials coming on the market. Because drifts extend as far as 35 times the height of a fence, the fence should be at least 35 h from the roadway. The end effect at the end of a fence and natural variation in winds can cause reduced capacity, but extending the fence length by 20 h on each end will offset it. Generally, fences should be perpendicular to the wind, but if winds are within 25 degrees of being perpendicular to the road, then the fence should be parallel to the road. Naturally, we can't cover all snow fence research results in this presentation. Detailed references are available in other publications such as design manuals and the Sharp Guide. Remember, research has shown that snow fence systems can significantly improve highway safety and reduce winter maintenance costs. Results from this sharp research can help solve your problems as well as provide improvements to existing programs.